All right, hi everyone. So we we're going to focus on another aspect of electrons. So in lesson 4, we talked about electron configuration and how the electrons are arranged in their energy levels and orbits or orbitals, the sublevels S, P, D, and F. And now we're going to talk about what happens when those electrons start moving around, okay? Because we talked about how each electron has its own place, but what happens when it moves out of its place, okay? And so these models on the left side of your screen and on your note sheet are all examples of Bohr's planetary model, and that's because our electrons are in orbitals, or it looks like they are orbiting the nucleus the way planets do the sun. So remember, at the center, you're going to have your protons and your neutrons in the nucleus, and your electrons are going to be in energy levels around it. Now, I'm just going to draw 2 electrons for now, and these electrons are in what we call the ground state. Okay, the ground state of an electron is the energy level that it's originally in, or it's normally in. Okay, so it's its regular place. It's also considered the state of the lowest energy for that particular electron. So for example, the first energy level could be the ground state for that electron. But if an electron is normally on the second energy level, then the second energy level would be the ground state for that particular electron. So the ground state is not always the first energy level, it's just whichever one it's normally in. Okay, now what happens is when those electrons, or the atom, is exposed to heat, or it absorbs a photon, which I don't know why the notes looked like this. Photons are a bundle of light particles, okay? So when atoms either absorb energy from heat, like through a flame, like in our flame test lab, or in any sort of thing, or it absorbs photons from the sun, things like that, the electrons can absorb all of that energy. So the way that looks, for example, is the energy comes into the atom and the electrons absorb the energy. So the energy is absorbed into the atom, okay? So this is step 1 of our process of light emission, is absorption. So the energy is absorbed by the electron. Now, when the electron absorbs the energy level, okay, energy level 1 only has so much energy. So if the electron has more energy than it did before, okay, then it can't stay there, okay? So that's because each energy level has a specific amount of energy associated with it. So when electrons absorb the energy, they move away from the nucleus to a higher energy orbital called the excited state. Okay, so their excited state is that energy level with the higher amount. So let's look at that original. So we had our protons and neutrons in the center of our atom, and we had 3 electrons in our original diagram. We had these 2, and then we have this electron that's absorbed energy. Now what happens is when it absorbs energy, that electron is going to move up away from it to a higher energy level. So this place right here, its higher energy level, that's the excited state, okay? It's usually on energy level number 1, but now it's on energy level number 3. And so that is a much higher energy level. And so these electrons have to have exactly the amount that they need, okay? They cannot move halfway to another energy level. So meaning that when they absorb energy, they have to have the exact amount needed to get to number 3. They can't go like halfway and then come back. Okay, they have to go all the way. They can only go from energy level 1 to 2 to 3. There's no such thing as moving to energy level 2.5. Okay, it has to go the full way. Now, the problem with this is that the excited state is unstable. Okay, imagine if you have little kids who are hyped up on candy, right? They've got a lot of energy from all the sugar. They're running around. They're very, very excited, okay? But they can't stay that way forever. So the excited state is only temporary, okay? It's not a permanent move, okay? And so the electron has to release energy to return to the ground state. So we know that little kids do that by running around and all of that. But when the electron releases energy, okay, which there's not supposed to be a blank there, okay? When the electron releases energy, it releases as colored light, okay? Which remember, light is a photon, okay? And so depending on how many energy levels it moves, the color of the light can change. So for example, when we think about light, think about Roy G. Biv, okay? Red, orange, yellow, green, blue, indigo, and violet. Hopefully, when you've seen fire, you've seen that like a campfire, for example, can have red and orange and yellow. You might see blue or white, okay? And each color represents a different amount of energy. So red energy or red light has low energy compared to down here. So this would be high energy. And so you can tell how much or what color light is being produced. That can tell you how much energy it is. So it goes from low to high down the color of rainbows. And so when it releases, okay, so emission just means to release, okay? So we see here that the energy is absorbed, it moves to the excited state, but when it's in its excited state, okay, so we've, again, in our model, we have our protons and neutrons in the center. We had these electrons here. Okay, our electron was originally in this third energy level, but to release it, what's going to happen is it's going to release colored light, okay, or a photon. And when it releases the light, it will move back to its original location or the ground state. Now, because all atoms have a unique pattern to the electrons, right? They all have their own electron configuration. They have their own number of electrons. This means that the type of light that atoms of that element produce is unique. So hydrogen is going to produce a different color light than lithium and sodium and copper. They all produce different ones. And so a flame test can be used like a fingerprint of the elements. It can help you identify different things. Now, I want to show you a different way of looking at the models. Sometimes you don't see an image of the full atom. Sometimes you see it kind of zoomed in, where these are your energy levels and they're just kind of stacked up. So, for example, this is energy level number 1, number 2, number 3, and number 4. So if we have an electron that's on energy level 1, right? Then step 1 would be, let's say that the energy is absorbed. So you have energy comes in, so step 1 is you absorb, right? And then step 2 is that electron is going to move up energy levels. So let's say it goes up to level number 3. Okay? Well, then the electron is going to have to come back down. And in order to do that, it's going to release light. So let's say it releases, yellow light. Okay? Oops, that's not yellow, that's purple. Okay? So it releases a photon. Okay? So step 1, it absorbs, it moves. Step 3, it releases, which is another word for that is emits a photon, and then it moves back down. Okay, and it does this over and over and over again really, really fast. Okay, so you might see it different ways. And so we kind of have our steps there. Now, on the back of your note sheet, you should have some just like practice. So you can see this is another version of that zoomed in one. And the question wants you to explain why we get different colors when we absorb energy, and it's just not always white light or red light. So kind of use this model on the left to help explain. And then here, you can kind of summarize some of your definitions. Now, these atomic emission spectrums, so the way these are produced is if you take light and you stick it into a prism, right? It can, when the light goes through, it bounces out into the different colors, like a rainbow. And so these prisms allow you to see these different lines. And so the atomic emission spectrum is unique for every element. So we can see we've got hydrogen and helium and neon and sodium and mercury. Okay, and they're going to produce different bands. And those bands represent the electrons that are moving from an excited energy level back to their ground state. And so those different movements among the levels produce unique light. So, why are these unique? Okay, what about each element makes them unique? And then it wants you to take this one and match it to one of these up here at the top because it's not labeled. So you should be able to use it as a way to identify it. So you can work on that practice and make sure that you are using this explanation for how electrons emit light to be able to explain your flame test lab.